Hello friends. When we were trying to codify some conditions for similarities in triangles, we said something very unique to triangles, right? That is, if in two triangles, corresponding angles are equal, then it implies that the corresponding sides are in the same ratio or proportion. And also its converse, that is, if in two triangles, corresponding sides are in the same ratio, then it implies that their corresponding angles are equal. Now to prove this by implication statement here, we need to state and prove a very important theorem in geometry, which is the basic proportionality theorem. Now we will see that this theorem will be very useful going forward. So here is how the statement is put in words. If a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, then the line divides the other sides in the same ratio. Now let's try to put this mathematically, right? Now if you have a triangle ABC and if you have a line parallel to the base BC to intersect these two sides at some points P and Q, then we have AP by PB is equal to AQ by QC. And this is when the line PQ is parallel to the side BC, right? So we can say given a triangle ABC where PQ is parallel to BC, then AP by PB is equal to AQ by QC. Now the main concept behind this proof is the fact that two triangles on the same base and between the same parallels have the same area. That is, if I have these two parallel lines with points AB on the top line and points CD on the bottom line, then I have triangle ACD and triangle BCD, right? Now these two have a common base which is CD and they are between the same parallel lines. And we know that the areas of this triangle and this triangle are the same because their height is the same because they lie in between the same parallel lines. So therefore area of triangle ACD is equal to area of triangle BCD is equal to half the base CD into the height, which is the distance between the parallel lines. Now what if in between the same two parallel lines, the two triangles don't have a same base? Now say there's a point A here and point BCD on the bottom line. Now I have a triangle ABC and triangle ACD. Now both have different bases which are BC and CD, but they have a common third vertex, right? Now since they are between the same parallel lines, we have the same height for both the triangles, which is the distance between the parallel lines. So the area of triangle ABC will be half into the base BC into the height, and area of triangle ACD is equal to half into the base CD into height. So therefore if I take the ratio of these areas, I get area of triangle ABC divided by area of triangle ACD is equal to the base BC by the base CD. So we will utilize this property and try to convert the ratio of lengths that we are supposed to prove in the theorem to a ratio of areas, and we'll try to prove this basic proportionality theorem. Now since we formulated the basic idea, let us go ahead with the proof. Now let us consider this triangle ABC. I have a line segment PQ that is parallel to BC, and we have to prove that AP by PB is equal to AQ by QC. Now we will write this left hand side AP by PB as some ratio of areas of some triangles that have bases as AP and PB. Now let us try to find those triangles that have bases AP and PB and that are between the same parallels. Now instead of finding triangles between the same parallels, you can also find triangles that have the same common third vertex, right? Now I already have the triangle APQ. Now if I can form this triangle PBQ by joining B to Q, then both these triangles have the same common vertex at Q. So they will have the same height, which is the perpendicular dropped from Q onto this particular side, right, which is AB. So therefore if I write ratio of triangle APQ and PBQ, I get half into base into height for the first triangle, which is half into AP into the height divided by half into the base of the second triangle, which is PB into height. So therefore I get area of triangle APQ divided by area of triangle PBQ is equal to AP by PB. This is our first equation. Now similarly, let's use the same logic and let's try to write the right hand side of what we have to prove as some ratio of areas of some triangles, right? So I have AQ by QC. Now I have to write this as some ratio of areas of triangles. and let me find two triangles that have bases as AQ and QC and that have the same common vertex, so they will have the same height, right? Now if I join C to P, I get two triangles AQP and triangle QCP. Now these two have the same common vertex at P, so they will have the same height, which is the perpendicular dropped from P onto this particular side, right? So therefore area of triangle AQP divided by area of triangle QCP is equal to half into the base of the first triangle, which is AQ, into the height, which is say H2, divided by half into the base of the second triangle, which is QC, into the same height H2. So I get the ratio as AQ by QC. This is my second equation. So we have written the left hand side as some ratio of areas of triangles and the right hand side as some ratio of areas of triangles. Now if you can prove that these two ratios of areas are the same, then our job is done. Now in these two ratios of areas, the numerator is the same, which is area of triangle APQ. But the denominator is different. In one I have the area of triangle PBQ and in the other I have area of triangle QCP. And if you can somehow show that the denominators are the same, then we can prove this theorem. So let us see if we can actually prove that point. Now I have this triangle PBQ and I have this triangle QCP. But wait a minute, I know that this line PQ is parallel to this line BC, which I haven't still yet used, right? And these two triangles are on the same common base, PQ, so they should have the same area, right? Because they are on the same base and between the same parallels, PQ and BC. So therefore, using that property, I can write that area of triangle PBQ and area of triangle QCP are the same, and hence these two ratios have to be the same. So therefore, I can say that AP by PB is equal to AQ by QC using 1 and 2, right? So did you see how we have actually proved this theorem quite easily? Now what do you think about the converse of the basic proportionality theorem? Well, it is true. So let's just quickly state the theorem and let's try to prove it. So the converse of the basic proportionality theorem goes as follows. If a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. So to put it geometrically, consider this triangle ABC. Suppose if I line PQ that divides both these sides in such that AP by PB is equal to AQ by QC. Then we should have the line PQ to be parallel to BC. That is given AP by PB is equal to AQ by QC to prove PQ is parallel to BC. Now you will see that the proof to this should be easy because we already proved the basic proportionality theorem. Now since we have to prove that PQ is parallel to BC, let us assume that it is actually not parallel to the base BC. Then there has to be some line passing through P that should be parallel to BC, right? Now say I draw this line PQ dash where Q dash is on this segment AC that is parallel to the base BC. So we have PQ dash parallel to BC. So can we use the basic proportionality theorem? Right? We can. So I can write that PQ dash divides both these sides in the same ratio, that is AP by PB is equal to AQ dash by Q dash C. This is the observation from the basic proportionality theorem that we have made because PQ dash is actually parallel to base BC. But from the given information, we already know that AP by PB is equal to AQ by QC. So by comparing these two equations, I can write AQ by QC is equal to AQ dash by Q dash C. Now if you look at the diagram, AQ by QC should be equal to AQ dash by Q dash C. So from this, it appears that Q and Q dash C should be the same point, right? But we cannot tell so clearly from this equation. So we will do a particular operation which is very, very important and we will use that a lot in this chapter. And the operation that we will do here is just add 1 to both sides of the equation. It's that simple. Now what happens if you add 1 to both sides? I get AQ by QC plus 1 is equal to AQ dash by Q dash C plus 1. Now let's take a common denominator. I got AQ plus QC whole by QC is equal to AQ dash plus Q dash C whole by QC. Now AQ plus QC is AC and AQ dash plus Q dash C is also AC. So I get AC by QC is equal to AC by Q dash C, or QC is equal to Q dash C. Now what does it mean? If QC is equal to Q dash C, then Q and Q dash should be the same point or they should coincide, right? And if they coincide, then since AQ dash is parallel to BC, we should have PQ also parallel to BC, right? So we have proved this theorem that PQ is parallel to BC when provided that AP by PB is equal to AQ by Q dash C. So friends, we have proved the basic proportionality theorem and its converse, which are the most fundamental theorems in this chapter. So in the next few sessions, we will see how we can apply these theorems and identify some important results, and also use these theorems to identify the criterion for similarity of triangles. But before that, let us quickly summarize. Basic proportionality theorem. If a line is drawn parallel to any one side of a triangle to intersect the other two sides in distinct points, then the other two sides are divided in the same ratio. Converse of the basic proportionality theorem. If a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side of the triangle.